Today I will speak in my talk about the atomistic modeling based on the phase field. So I'm very glad that just before me you introduced already the phase field modeling, and in our work we ask the same question: how we can use the advantage of the phase field approach and go to the microscopic scale to describe the interface. But first of all, I would like to thank my co-collaborator, my colleagues from University of Rouen. It's Gilles Demange, my postdoctoral student, Mikola Lavsky, actual PhD student, and somebody who don't like to be photographed. So we did a Fourier transform. If you know how to do inverse Fourier transform, you will find So, and also I would like to thank to Professor Khachaturian from Rutgers University, who is a pioneer in phase field modeling approach, and very long, very numerous discussion with him give us the driving force to create this new method, and also give a lot of idea how to do. So if you think about the macroscopic structure of alloys, the macroscopic properties, many times it was underlined that it depends from the macrostructure. And this macrostructure is a result of many phase transformation in real alloys. And for example, it can be like order-disorder phase transformation or phase separation. And in this picture, you can see just a very known microstructure, which we call rafting structure in nickel-based alloys, which really induce a very good mechanical properties of these materials. And in this case, we can see the cuboidal L12 ordering structure, which align to some elastically soft direction. So in this case, phase field modeling can be applied, traditional, I would like to say, phase field modeling, to understand how it happens. It means that in this case, we should introduce the influence of elastic energy, and we can see that during the coarsening phenomena, in red it's the ordering structure, in black it's the matrix, the precipitates will align to some elastically soft direction and create this rafting structure, which is quite useful if we would like to increase the mechanical properties of materials. However, in steels, the phase transformation, which is responsible to the microstructure, is related mostly to displacive phase transformation. In this case, if we quench the austenite high temperature phase, which has the FCC structure, during very rapid quenching, we can obtain the martensite phase, and during slow quenching or aging, we obtain the ferrite. And in this picture, you can see the very complex steel structure, which contains all these three phases. So retain austenite phase, the ferrite phase, martensite phase, and sometimes intermediate HCP phase. So to really understand what happens in steels, it's quite complicated, because first of all, we have the redistribution of the carbon atom, which is a main element also of steels, and also plus this displacive phase transformation. However, the phase field modeling, at least traditional phase field modeling, again at mesoscopic scale, now is able to describe, for example, here the growth of the martensite phase in the polycrystal. Here it was the simulation of cubic to trigonal martensitic transformation, and the different color represents the different variant of martensite phase. And we can predict what is the microstructure in this different point, and describe the hysteresis loops on the strain stress curve for some given materials. However, as was evocated just in previous talk, many mechanical properties and many global macroscopic properties of materials are related to interaction of the dislocation with the interface. And especially, we should think that interface is not really a pure interface in this kind of materials, because there is a lot of segregation in the interface. And in this case, it can change completely the properties in the grain boundaries, for example, of dislocation movement. In this picture, you can see the atom probe tomography picture analysis of HPT steels, higher pressure torsion steel. aging at 400 degrees C, and we can see clearly the segregation of the solute atoms like molybdenum or silicium will completely change the properties of this interface. So this is why to really explain something, to understand clearly the macroscopic properties of materials, we need to go to microscopic scale, and in our case, we try to do this based on the completely phase field description, not go to the Monte Carlo or maybe increase the length scale of molecular dynamic simulation. We decided to stay in this phenomenology of phase field and to try to develop some method which be able to describe this system at atomistic scale. So if you think about the phase field, of course, it's based on the Landau-Kalatnikov relaxation equation, which just shows that if you do some fluctuation, it will relax linearly with the driving force, and the free energy is a function, non-linear function of this parameter of C. Then this, in 70s, this Landau-Kalatnikov relaxation equation, I don't know if everybody knows, was written already at atomistic scale, and we call it as macroscopic kinetic equation, on very close to Onzager equation, where we work not with the field of concentration of the order parameter, we work with the probability function. It means that this probability function is the probability to find atom at some given position. It's the mean value of the jump of the atoms. If you take the configuration, you have the Gibbs average, you will obtain this probability function. And so this probability function can be calculated at a given time using this Landau-Kalatnikov relaxation equation, and I will give you some example which it can be done, and we can calculate, for example, order-disorder phase transformation, but the problem in this case, we work in the discrete scale. It means that it's like in Monte Carlo, the probability jump from one side to another side for a given crystallographic structure, FCC or BCC. And some continuous description, if we go from the Landau-Kalatnikov equation with continuous case, as was shown just before, that we work with two fields, the order parameter field, which can be associated to many things. It can be the strain, it can be the open the crack, it can be the density, and also it can be associated to the concentration field, and solving these two equations, we can calculate the macrostructure evolution. The problem, as I say, how to combine this advantage from discrete solution and microscopic scale and continuous solution, but at mesoscopic scale, and create something which be able to describe the macroscopic scale, but in continuous space. Why continuous? Because we are interested about the, for example, dislocation of the interface, or something which is not really periodicity of the crystal structure. This can be done by two ways. First of all, if we think about phase field, as I say, that at the beginning it was, I would like to say, mesoscopic phase scale, and then it was developed to atomic density function theory. And recently, I suppose you know, or you listen maybe, that it was done also from phase field to go to continuous scale at atomic scale. It was phase field crystal method. It means that if we go down from the mesh, the resolution of the mesh, and we change a little bit the free energy, I will show you how we can do this. We can go from this mesoscopic description directly to some microscopic description and continuous scale. But we can do also this from different way. We can go from the discrete description and using the atomic density function, and to go to this direction and also produce some method which is able to work at macroscopic scale and in continuous space. So we call this quasi-particle approach. First of all, to describe a little bit how PFC, phase field crystal method, was done, and why it's can be one, he can describe the atomistic resolution. Just to remember that the free energy in the phase field contain contains two terms. First term is the homogeneous free energy, which describes the coexisting phase, and the second one is the interface, of course, interface which is defined by the gradient square, and the beta is the proportional of the energy of the interface. Then if we introduce a small fluctuation in the system, which should relax normally with Landau-Ginzburg equation, we can go to the reciprocal space, and this fluctuation we can write in the reciprocal space using just Fourier transform. And in this case, the variation of free energy with respect to this small fluctuation can be written using this form, which bk, it will be just k squared plus the Fourier transform of this function. So it's some Gaussian function, but a little bit deformed because we do the Fourier transform on Vc. And in this case, the minima of the delta f will be related to the minima of bk. And if you look in this function bk, which, as I say, is proportional to k squared because we have the gradient, in real space we have the gradient square, so it can have the two situations. The first situation, if the minima of this function is situated at k equals 0, we will have the separation dynamics because the AB atom or AB concentration will go as far as possible because the minima it's infinite. K equals 0, R equals infinite. And if its B function, its minima is some given K0, the system will produce some periodic structure, as you can see here, where the precipitates will be exactly the same size and arranged by this honeycomb structure. And this, it was idea also proposed by Brazovsky in 70s to describe that crystallization phenomena. To describe this periodic honeycomb structure, Brazovsky proposed to introduce in the Landau free energy additional term, C cube, which is breaks the symmetry, which negative and positive will be different, and also add some gradient 4. Using this expression, we can see that this bk function, which is final response function in this case, will have the minima at k equals 0, it given k, which is we can see here, and we obtain some periodic structure which Brazovsky associated to the crystallization. So if we go from some homogeneous state to some periodic state, we can describe this using this kind of free energy, and then Swift-Hohenberg, using this free energy, which gradient 4 and gradient 2, plus this shift K0, describe the pattern formation during the Rayleigh-Bernard convection. Well, the phase field modeling is something very phenomenological modeling, so we can apply for the different phenomena, not only for the phase transformation and solid, of course. And using this, Ken Elder in 2002 proposed a very interesting idea that he says that if this equation, like Swift-Hohenberg equation, give us some periodic structure, as you can see here, we will interpret the concentration, higher concentration region like atoms. And then if we introduce the interaction between this higher concentration zone, we will have the atoms which move in continuous space. So finally, idea is very simple but very nice, and this is was the beginning of phase field crystal modeling. And now there is a lot of people who use it and introduce some kind of interaction here. And now it's done in 3D. We can describe the different crystal structure, FCC, BCC, hexagonal structure, etc. The advantage of this that we can really work in the atomic system and in continuous space. The atom can move everywhere. It's not like in discrete lattice where the atom can just jump from one to another crystal site. The problem of this description is that sometimes we can obtain the stripe structure. It means that if the driving force is very high, we can go from the honeycomb structure to the stripe structure. And this, it was one of the problems of this approach at the beginning. But globally, if we would like to understand what is the link between the microscopic description and this phase field crystal model, we can just think about the free energy which contains some homogeneous part and some interaction part. And if we develop the interaction Vk Fourier transform of interaction with respect to the Taylor series, and we cut in the term 4, we obtain exactly the expression of free energy in the phase field crystal. So it means that there is a link between this microscopic description and microscopic description, because it just is a Taylor description. For example, if I cut here K2, it's a traditional phase field modeling. If we will cut K4, the mesh of the simulation will be smaller. And in this case, we go to this PFC crystal modeling. However, in our case, we wanted to evitate this stripe structure, and we have some experience in the microscopic phase field in the discrete lattice, and we decided to develop this method from the atomic density function. So come back to this. The second way to develop this phase field atomistic approach, we can start with this notion of the probability function, and the free energy, chemical free energy, can be written in this case using the mean field approximation. We have this pair interaction between the probability PR prime and the entropy term. And here we can also include the elastic energy like in phase field, but Bn, I will precise in the next slide, can be also written its atomistic scale using the Kanzaki forces. So using the atomistic equation, Landau-Kalatnikov equation at atomistic scale, we can solve this kinetic equation and obtain the different evolution, for example, of this, in this case, is a carbon atom which diffuse on the in the Martensite BCC lattice. So in more detail, I would like to just to show you how it works. It's a discrete lattice. For example, this example related to the diffusion of the carbon atoms in the BCC lattice. So it's well known that in this case, we will have the 3 octahedral interstitial site. And normally, when we quench our alloys, the carbon atom are distributed only on the one sublattices, what we call the Zener ordering, and it's produced some tetragonal dilatation. And in this case, so to describe all of this, we introduce the concentration expansion coefficient, which is a difference between the lattice parameter in the Martensite phase and initial BCC ferrite phase. And then we can write the deformation matrix. It's just cubic matrix, so there is only the tetragonal elements. And then the interaction parameter in this case will contain the elastic part and chemical part. So for the elastic part, the Eshelby free energy can be written using the Kanzaki forces. So elastic energy will be product of the Kanzaki forces multiplied by the green function, which is inverse of the dynamic matrix. And these Kanzaki forces, the physical meaning of this is the force at which the carbon atom push the surrounding iron atoms. So we can write this for the given symmetry, and in our case, for the BCC case, it will have this kind of expression. And then we should introduce also the chemical energy. So the chemical energy we introduce until for neighbor, and all this parameter, which is thermodynamic parameter, we extracted from ab initio calculation. It means that the first neighbor, second neighbor, etc. And it was calculated in this work from ab initio data. The free energy, the energy of interaction at different in different interaction and in different distance. Then put together, we use a dimensionless parameter, which is a dimensional parameter, which is just a lattice parameter, elastic constant, and misfit, and then using this Onsager equation or microscopic kinetic equation, we can calculate the evolution of the carbon atoms on this octahedral interstice and obtain the segregation of some carbon atom in some particular direction. And what is good in our case, because we are working with a group in our laboratory who is specialist in 3D atom probe analysis, so we have at the same scale the experimental data, and we can compare directly our result with the experimental data obtained from 3D APT analysis. What is also interesting, what we obtained, which is in the beginning we don't think to have, it's the creation of some metastable carbide. Because in iron carbon system, of course it's a system which is maybe a more studied system because it's the base of the all steels. There is a many open question related to the metastable carbide. We don't know exactly what is the link between these. There is a lot of measurements, there is a lot of concentration, there is a lot of crystal. And in our case, we can show that the link between all this metastable carbide may be associated to the Magnelli phases. Magnelli phases where the carbon atom occupy first the 110 plane, and then if you increase the concentration inside of the precipitate, the carbon atom will be occupy the second sublattices, etc. And we create this metastable carbide, which can be related with this chemical formula, which is related to the Magnelli phases. And what is also advantage of this microscopic description, that we can calculate the diffraction pattern. Because experimental data mostly related to diffraction pattern if you study some order-disorder phase transformation. And in this case, we can, here you can see the experimental diffraction pattern, which is, was obtained for the iron-nickel carbon martensite. And we can see some special alignment to some special direction, which is related to the tetragonal deformation of this carbon-rich phase. And in our simulation, we obtain the same kind of diffraction spots. And related to this, we can calculate the angle between the main direction, for example, 100, and this alignment of this diffraction spot, and obtain data in compare with experimental data. What it means that if we calculate this, we can really compare by quantitative way the alignment of this carbon-rich zone from experiments and from simulation data. It was also done, so if we continue our simulation, we will obtain the iron-2 carbon phase, which you can see here. And in this case, as I say, the carbon atom will occupy two different sublattices, octahedral sublattices, which you can see here. And we describe quite nicely the microstructure of this iron-2 carbon phase, which you can see here in experimental data. So we have the alignment to some special direction, which also, of course, governed by the elasticity, by elastic energy, which was included here. And we can link, in this case, the structure of this iron-2 carbon carbide with another type of carbide. So now, how it's good, but I say at the beginning, the idea it's not really stay at the discrete level, but try to go to some continuous space. And in this case, it was proposed to, for example, here, what it means discrete case for us. It means that we mesh our simulation box with some points, and at each point we will put the atoms. And then the evolution of the probability just will change the probability at each side. If we go to some continuous model, we will take the simulation mesh is much smaller than the distance between the atoms. And in this case, there is some, I would like to say, not artifact, but need to think that atoms start to be a sphere. It's not just a point. Is a sphere, and some number of mesh of your simulation will be inside of this sphere. So the concentration now is not just the sum of the probability, it's the number of this mesh which are inside of all atoms. It means, for example, here we have we have some number of atoms for each atom. And if I would like to create 5 atoms, I should multiply the number of the simulation grid inside of the sphere by the number of atoms, and this is my initial density. So this is a difference between this kind of approach and the discrete approach. And we call it this a fraton, is fraction of atom. It's not really fraction of atom, just to introduce some name to know how to introduce the density. So in this case, we start with the density of fraton, not density of atoms. It can be recalculated if we fix the atomic radius, but anyway, it should be noted that it should be careful in this case of modeling. So how about the interaction in this case? Because now we have the atom which has some size, and we have the interaction between the atoms. This is why we need to introduce the two kinds of interactions: the short-range interaction, which you can see here, and the long-range interaction. So the short-range interaction, it was introduced by the step function to fix the size of the atoms. Why? Because in the PFC method, as I say, there is no this short-range interaction, and if we work with some big driving force, the atoms start to be line. It's stripe structure. To avoid this, we introduce a short-range interaction to really fix the size of the atom. First of all, it's avoid to do the stripe. And secondary, we can work with the different sort of atoms. We can increase or decrease the size of the atom if you would like, because this it will be imposed by this short-range interaction. So the short-range interaction is, as I say, the step function, which is a reciprocal space, has this form. And long-range interaction, it was fitted by the, it's two ways to fit this. This is example with Gaussian function. And in other way, we can calculate from the scattering function, because the scattering function is the inverse function of the our response function. So this is one example which we use now. So it's a minima, which is correspond to the lattice parameter which we, of our crystal structure, and the depth of this function, which should be proportional to the temperature. So this thickness of this Gaussian also will influence the elastic properties of our materials. So to test, for example, we choose some Gaussian function, and we would like to know if we can describe our real materials. Here is just to show how we proceed. It means that we apply the heterostatic, orthorhombic, and monoclinic deformation. In the first case, we can obtain the evolution of the free energy, which is proportional to the bulk modulus, C11 plus 2 C12 for the cubic system. It's just an example. Then we have some orthorhombic deformation, which give us C11 minus C12, and the shear monoclinic deformation can give us the C44. So we adjust our thickness of our Gaussian to obtain the elastic constant for the material at which we are interested. And also, I need to say that number of minima correspond to the number of high symmetry point in the first Brillouin zone. It means that we know that in crystallography, we know that the symmetry of the crystal corresponds, for example, if I do the diffraction of FCC, I will obtain BCC, which is the point 111 and 200. So I should put the minima of my Gaussian to this point. If I take FCC, or BCC, I will obtain FCC, etc. So the number of minima corresponds to the number of high symmetry points in the first Brillouin zone for a given crystal. For example, I will show you an example for the BCC, for the FCC. For BCC, we take only one minima. For FCC, to describe the structure, we have two minima. For the cubic structure, we take three minima, etc. For the hexagonal, we can do another things. So once we accept that it's possible to work, so we write the free energy, as I say, in mean field approximation, where Vk contains this short-range and long-range interaction. We have also the entropy term. And the adimensional parameter will be the time scale is measured in typical atomic migration time. Energy is unit kBT0, with T0 is the solidification temperature, and the grid lattice is just the fraction of the distance between the atoms. And we solve our equation using the semi-implicit Fourier spectral method, which is very useful, very interesting because we can parallelize our simulation and it's very fast. So just to show you what it gives, for example, if I take only the short range. The short range, it means that there is no crystallographic structure. And this, if I start with some homogeneous distribution of my photons, I will obtain some number of atoms, just atoms by randomly distributed in my simulation box. And if I increase the density at the beginning, I will go from disordering state to FCC state at the end, because FCC is more compact phase and it will appear immediately. So we can simulate, I would like to say, the amorphous state or gas state. If I add the periodic structure, in this case, for example, we calculated the interface structure at grain boundaries in alpha iron. In this case, we introduce the short-range interaction, which correspond to the size of the iron, and also the long-range interaction with one minima, because we are interested about the BCC crystal. And this long-range interaction, in this case, was adjusted with respect to the molecular dynamic calculation of the structural factor, which you can see here. And then we tested the elastic constant C11, C12 in bulk modulus to be sure that our potential reproduce the elastic properties of our materials. So using this, the initial configuration in this case, it will be two crystal which is rotated to some special angle, and we put inside between both the liquid, because we not like in molecular dynamics, we don't relax near some configuration. We put a really liquid and we don't know what we obtain. It means that liquid is crystallized and it will be minimal free energy, which will dictate what is the crystal structure of our grain boundary. In this case, it's theta equal 3.58, and we obtain the two grain boundary dislocation, which is usually obtained by molecular dynamic simulation. And follow this way, we can obtain the configuration of all this grain boundary, as you can see here. And in our case, we calculate the structure of grain boundary in the high temperature, so 0.9 melting. And of course, at this temperature, the energy of grain boundary cannot be the same like in molecular dynamics at T equals 0. This is why we relax our structure using the molecular dynamic simulation at T equals 0. And here you can see that it's reproduced exactly the energy of, obtained by CHOP, who use just pure molecular dynamic simulation. And this gives us some idea what happens with the grain boundary in the high temperature. So as you can see, some grain boundary will be increased, the free energy of grain boundary, and some of them will decrease. So I think it can be very useful if we work with the real materials and not, of course, at K equals 0. So in this case, we can predict what will be the evolution of the grain boundary at different temperature. Recently, we also applied this method to understand the segregation of the different sort of atoms at the grain boundary in alpha iron. In this case, we choose the three kinds of atoms with a different radius, the radius bigger and smaller of iron. It can be associated, for example, for the first kind of atom, which the radius is smaller, it's phosphorus atom, which usually present in the many steel. And also, if radius approximately equal radius of iron, it's antimony. And we also consider it atom which is biggest radius of iron, so it's tin. Then we study the two grain boundary, low angle grain boundary and high angle grain boundaries. And in this case, the interaction, the short range interaction will be shifted each time because the size of the atom is different. And the long range interaction has one minima because it's a BCC structure. And we suppose that interaction between iron and solid atom is just the phase separation. There is no some ordering structure. If phase separation, it means that we take the potential which at K equals 0 minima. k equals 0. I repeat again that if we take the interaction at k equals 0 negative, it means the atom will try to go as far as possible, because k equals 0, r equals infinite. So we'll push atoms far from each other. So do this, we can obtain the quadral atmosphere, what we call the quadral atmosphere, the segregation of the solute atom near the dislocation in the case of the low angle grain boundaries. Here you can see these segregated atoms. For the atom x1 and x2, it means the smallest radius and approximately the same radius as the iron atoms. And we see that there is a quite a difference. Of course, we find some decoration of the dilatation region, but near the core of dislocation, we see that it's quite a different position of the segregated atoms. For the higher angle ground boundary, there is no, of course, dislocation. There is some structural units. And in this case, we find that the different sort of atom will create some cupped trigonal prism, as you can see here. So this is the smallest one in the bigger and more bigger atoms. So the solute atom will move from the middle approximately of this trigonal prism to the outside because it starts to be more and more bigger. And another interesting phenomena that the zone where the atoms are segregated at grain boundary will be smaller and smaller. It means if you go to the big size of the atoms, they will be segregated really along the grain boundary, but not in the volume, because in the grain boundary, in this case, we will have the region with the dilatation. Then what is nice in this method, as I say, we can solve easily using the Fourier transform semi-implicit method. And in this case, we can work with the simulation boxes around 3,000 cube, which give us a big volume to, for example, produce the polycrystal. And here just you see the polycrystal again in alpha iron, and some grain boundaries are decorated by the dislocation. This is an elastic field around this dislocation. And just to show you how this evolves with time, it means that we hit and the grains start to course. And we can see that this is just one plane to this simulation. We can see that there is emission of some dislocation. For example, here you will see that one dislocation will be emitted from the grain boundary. Another one will move in this field, and after will coagulate and after disappear of the grain boundary in the end. So this gives us this possibility to be, I would like to say, free to describe this polycrystal at the big simulation, in big simulation box, and also to go to diffusion time. We also tested our method to understand what is the influence of applied stress on the structure of grain boundary, because in most of cases we calculate the structure of grain boundary, and after we just consider that if we apply the elastic field, we just will interact the dislocation with some given structure of grain boundary. In our case, at least for the iron, alpha iron, we see, for example, that if we apply the uniaxial elastic stress, is compression, we will see that the structural unit will be modified and will be completely different. I suppose the interaction with the dislocation will be very different, and of course the energy of this grain boundary will change. And for example, for this kind of grain boundary, 46, it's a 29 grain boundary, we can see that the different elements of the grain boundary will have the different reaction. For example, in this case, the C structure will not change approximately, as well as B will change and transform to the what we call A structure. So I would like to say that conclusion from this that we should be very careful if we work with the grain boundary and we applied elastic stress. It's not the grain boundary which we calculate in free samples. Then I would like to also show you that it can be also given insight of the Martin-Cytic transformation. As I said, the Martin-Cytic transformation is the main transformation path from the mostly of steels. And to understand this is very important. Just to remember that if I speak about the Martin-Cytic transformation, I think about the Bain model. At the beginning, at the high temperature, we have the FCC structure. And then during cooling, we have the rotation of this FCC structure, as you can see here. We obtain the BCC1. And then by compression, we obtain the, at the beginning is BCT. If we just rotate our crystal structure, we obtain the BCT structure, and then during the compression, we obtain the BCC1. So it can be done by different kind of rotation. There is many different plane, and totally for a given 111 FCC plane, we have the 6 different variant of this Martin-Cytic phase, and globally as well as we have the 4 different crystal plane 111, we will have 24 variant of the Martin-Cytic phase. And to model this, we introduce the long-range interaction in our case. So we have the BCC structure with is only we should put the 1 minima potential, and FCC1 is 2 minima potential. Then we test our elastic constant because we introduce some sigma, of course, some special sigma which related to the elastic constant, and the best what is we could do. For example, the relation between the BCC FCC, this is for our potential, and this is what is done from experimental data. So we can see that, for example, CYN1 it's approximately okay. And what is more different, it's C44. At least with just Gaussian function, it's the best what we can obtain. Then we applied this to describe the Martin-Cytic transformation and copper iron alloys. In this case, experimentally, it was observed that inside of the alpha-rich precipitates, we observed some number of variant, some twinning structure of the Martin-Cytic, as you can see here. And high-resolution images show us the interface between the different variant, V1, EV2. So to model this, we introduce in big simulation box, we introduce a small nucleus of the Kurt-Zumov-Sachs orientation relaxation BCC phase. And then we follow the growth of this. And the second variant appears automatically, so it's not by hand. It's really, if we introduce one variant of Kurt-Zumov-Sachs, during the growth, to minimize the free energy between the Martin-Cytic and quiver-rich matrix, we observe the appearance of this multivariant structure, as you can see here. And finally, the final structure will contain this periodic variant V1, V2. It depends also what is a Kurt-Zumov-Sachs variant. Oh, sorry, Kurt-Zumov-Sachs variant we put at the beginning. If I take first variant, it will be first, for example, a second. If I put third variant, it will be third, a fourth, etc. So to understand better what happens, we look more precisely on the interface between the two variants. As you can see here, we obtain some kink structure. And that kink structure can be related with two kinds of twin boundary. It can be a reflection, as you can see here, of isocell, it's thus shifting a little bit. And the propagation of this interface can be related to the propagation of the dislocation, in this case, and the stacking fault. Because to go from FCC to BCC, we should introduce a stacking fault, what we observed in this kind of modeling. And the interface will move to the -211 direction, which is a perpendicular to the twinning plane. And the step of this kink, it's approximately 2 square root of 6a2, which is the latest parameter of the BCC phase. So if you look in the interface between the FCC and BCC, not between the different variant, this method also gives us a very nice structure, which we can see. And first of all, we remark that there is some plateau between the FCC and BCC phase. It means that this I show just this BCC variant in front of the FCC matrix. And we also can identify using the Ovito that in the border of this interface, we have some number of screw dislocation with Burger vectors 1/2, 110 in the FCC reference. So it's decorated by this kind of screw dislocation and with some periodicity, which we can see here. And if we change the misfeed between the FCC and BCC phase, of course, this periodicity will change. So we really see this very nicely decorated, the screw dislocation structure. This structure can be also see, for example, if we look in some special place and we calculate the displacement of each atoms. So here we have the dislocation line, and we see clearly that it's a screw nature of the dislocation that you can see here around some point. And to understand how they propagate this interface between FCC and BCC, globally what we observe that in these steps, which we see between the FCC and BCC phase, we observe so the two kind of screw dislocation, plus minus 1/2, minus 100, and 1 minus 10. So this is the Burger's vector of these two kind of dislocation, and also the partial Shockley dislocation which induce the stacking fault, which is shown here. So what we at least observe in this case, the mechanism of this transformation is linked with the movement of Shockley partial dislocation with Burger's vector BP, and this movement of this Shockley dislocation will transform the ABC sequence on 1, FCC plane to A, B, and B, which we find in the BCC plane. And then we should have the contraction, because at the beginning we have the tetragonal. If you just A, B, it will be tetragonal. So this contraction is related to some screw dislocation to really decrease this X the tetragonal axis. And I have 3 minutes, yes. Okay, just to show you that for the duplex steel, it means that where we have a mixture of the ferrite and austenite phase, we can calculate, I will not go to the more detail, calculate the segregation of the solid atom at the interface in the different interface between the FCC and BCC phase. First of all, we are modeling the plane interface between the green is the FCC, blue is the BCC, and we can see that if you have the different orientation relations, the structure of the interface will be completely different, and the nature of dislocation will be completely changed, and I would like to transformation path also will be different. And here, for example, you can see the propagation of the Kurdumov-Sachs interface. And we can see that there is some number of kink which will be propagates, and growth, it looks like the propagation of kinks in some up to growth the jog. So just the last slide. Just to show you that globally the interface between plane interface between FCC and BCC phase can be characterized by this like step morphology when we find some number of kinks, some tirars, 1, tirars, and the line or dislocation line. So of course, if you change the habit plane, we will change this structure of the step. And now, recently, we did the dislocation analysis to really understand how it moves. So this is a field of the movement of dislocation. And yes, just to show you that it's possible also to add additional elements, the solute atom, and obtain the segregation. For example, here the carbon atoms at the during the transformation, FCC-BCC transformation. So just to finish, I would like to show you the very nice picture which we obtain for the facial modeling. It doesn't to do with my speech, but with this sunny sky, I would like to show you the snowflakes. We did a very nice modeling snowflakes. I like it so much that I would like to show you too. And just to show you that facial modeling is really capable to capture very, very complex morphology. For example, in this case, we have the growth of the normal flakes. And in the next one, it's some tube flakes, as you can see here. So it was for the fun, it was for the airspace industry. Okay, thank you so much.